Hello and welcome to this movie about diode large signal impedance. AC or complex impedances have already been defined for resistors, inductors and capacitors, but have not been defined for diodes. Is it ever possible that we may find a large signal linear impedance for a diode, so that we can plug it into a circuit matrix and easily solve a circuit with a diode, like for example a half-wave rectifier? Well, the thing is that the linear circuit elements have impedances that manipulate a sinusoid waveform in the circuit, either shifting it to the left or to the right, or making its amplitude larger or smaller. But a diode will not preserve the shape of the sinusoid. A voltage applied to it will get distorted. This can be taken to mean that a lot more frequencies and even a constant function will be needed to describe the output of a diode and to describe its impedance. It can't be done with a single frequency. So we'll have to redefine impedances so as to be able to create a large signal impedance for a diode. One way is to use time sampling. We can use time-sampled voltages and currents, and time-sampling impedance matrices. Here is an example of a time-sampled AC voltage, and though it is functional, it looks very rough, and doesn't describe a sinusoid voltage all that well, mostly because there aren't enough voltage samples per cycle. Here is a second example of a time-sampled voltage. There are more samples per interval, and the curve looks a lot better, although it looks rough at the peaks. Here is a third example of a time-sampled voltage, and has enough intervals for the curve to look nice enough to be accurately described. Here is what the time-sampled impedance would look like for a resistor. Resistors are able to be described by a multiple of the identity matrix for any combination of waveforms. This sort of impedance for an inductor would be described well by this matrix. It is made up of 5-point stencils, so as to fairly accurately describe a voltage or current being differentiated. Notice the n written as the denominator outside the matrix. It is the number of rows and columns in this matrix, which is 8. This is put in to help rescale the matrix to give the correct impedance. Here is the impedance for a capacitor. It uses a matrix that integrates a voltage or current over time. It uses Simpson's 3/8 rule and can be generally expanded to any size of matrix. It has a large value for the diagonal to force the DC value to be 0 for the voltage across it or the current through it. When solving circuits using a computer, admittances are calculated and used, because node voltage analysis is the naturally easier method to use, and admittances are plugged into the circuit matrix to solve for voltages in all nodes in the circuit. In this case we'll use block matrices to solve a circuit matrix, treating an admittance matrix as a single element in the circuit matrix. The admittance for a resistor is just the reciprocal of the resistance multiplied by the identity matrix. Here is the admittance matrix for an inductor. This time the inductor uses the integration matrix formed when using Simpson's 3/8 rule. And similarly, the admittance of a capacitor is a term multiplied by the differentiation matrix formed by point stencils. Now we are in a better position to find the time-sampled impedance and admittance matrices for a diode. Because a diode is time invariant, then it will be a diagonal matrix. And because it will either have near zero or near infinite resistance at any one moment in time, then it will be a diagonal matrix made up of very small and very large values. These values can be found by examining the conduction zone of a diode. The conduction zone occurs as a collection of sampled times that are next to each other. During the part of the cycle that is in the conduction zone, the values in this matrix will be very low, like 1/1,000,000th of an ohm. Outside this zone, they will be very high, like 1,000,000 ohms or a mega ohm, or higher if the load resistance is high. It must in any case be much higher than the load resistance. Here is an example of a half-wave rectifier voltage output across the load. This rectifier has a low load capacitance and has a large ripple. It is during the conduction zone here that the diode has a small resistance, and outside it that it has a large resistance. The conduction zone varies for different load capacitance resistance ratios. Here is the conduction zone for a half-wave rectifier with a larger load capacitance by a factor of 7. Notice that it has shrunk, and so has the ripple. The diode impedance varies with different conditions, but seems to have a fairly regular behavior. Here it is with an even higher load capacitance, and its conduction zone has shrunk, but not too much. The ripple shrinks as well. Here it is for an even higher load capacitance. Notice that the curve can't be easily described by this many intervals. And here it is for a very large load capacitance, so that it looks very rough for this amount of intervals, and could disappear altogether for very high capacitances. Even though the conduction zone does change a lot over this operating point, it doesn't make a real lot of difference if the conduction zone is too much larger or smaller. So it is possible to construct a time-sampled admittance matrix for a diode that is flexible enough to give a good range of approximate values around it to be used in a circuit matrix. And even though it doesn't work well for a rectifier with a big ripple, nobody is interested in using or analyzing this sort of rectifier anyway. Here is the high ripple output voltage for a bridge rectifier. Notice that it has two conduction zones, one for each pair of diodes. The first conduction zone is different but very similar to the conduction zone of a half-wave rectifier, and may be well approximated by this diode. The second conduction zone is the first one shifted by half a cycle or pi. It always has a smaller ripple than for a half-wave rectifier because the diodes conduct twice per cycle. Here are the two conduction zones for a higher load capacitor. And here it is for a very high capacitance, and it shrinks just like for a half-wave rectifier. Here is an example of a diode time sampling impedance. Here it is as an 8 by 8 matrix. This is the impedance for a diode in a half-wave rectifier, and for the first pathway in a bridge rectifier, and for an input of sine omega t. The diagonal elements are arranged so as to be very low during the conduction zone and very high outside it. I've given a good theoretical way of describing this matrix. The ith diagonal element is low if it is between 1.4 and 2.2, and high otherwise. Here is the corresponding impedance for the diodes in the second pathway of a bridge rectifier. It is shifted by half a cycle, and its theoretical description is as shown below, being similar to the first diode impedance. And here are the diode admittances that will be plugged into the circuit matrix, so as the circuits can be solved using the node voltage method. They are matrix inverses of the diode impedances. Here is the output of a circuit for a half-wave rectifier simulator using this diode impedance ZD1 as described, but for a 20 times sampled input of a 10 volt sine function voltage. Notice that it gives a good and fairly smooth DC output with a little bit of an oscillation. I've written a script of the circuit in SPICE notation at the bottom of the screen. Here is the output of a circuit for a bridge rectifier simulator using both diode impedances ZD1 and ZD2 as described, and the same input of a 10 volt sine function voltage. It produces a good 10 volt DC output voltage, so the diode impedances work well here to accurately describe the behaviour of a bridge rectifier circuit. Here is the output of a circuit for a half-wave rectifier simulator with an inductor in series, and also the output voltage across the inductor. Notice that the inductor gives the characteristic spike in voltage that it normally always gives. The output voltage is also affected, giving a lot of oscillation. To make other types of diode impedances, like frequency sampled impedance, it only requires the multiplication of the time sampled matrix impedance by two other matrices on either side of it. The matrix used on the right side would be the fast Fourier transform matrix, and on its left would be its inverse, as shown in the red box below. The construction of this matrix is shown for a sample of 8. It may be expanded for any number of samples. It may be possible to form different sorts of these matrices using a wide variety of waveforms, and to select which one is best. Here are the numerical values for the 7x7 fast Fourier transform matrix and its inverse. And here is the value of the frequency sampled impedance for a diode. By multiplying this matrix with the Fourier transform matrices, I get this new matrix at the bottom called ZW2, which looks very unstable and like it wouldn't work very well. It would need more frequencies at least, and I haven't checked it yet anyway. I don't think that a matrix based on frequencies is a good way to analyze diodes, because I did play around with them in the past. This is just to have a rough look at it. The time-sampled approach is the best, but there might be much better waveforms out there to make a diode impedance with.